Welcome back, everybody. I just handed back the exams. So you'll see that there's a score there's an initial score, and then there's an arrow to a new score that's circled. The arrowed score, that is the correct score, the score that you got. I am not infallible. I do realize that this exam was more challenging than the first one. Material can be more challenging in this section too, Victor. Um, but at the same time, it's also can take a little longer. And so this exam was a little bit longer than I anticipated. And so to kind of counterbalance that, I decided to curve the course a little bit. I decided to up the grades based on a little bit of few calculations. So it should have improved your score by a decent margin. Like if you were below or at the average, and then people at the who are at the higher end, you wouldn't have gotten as much because it's not like it's trying to redistribute the scores, and the people at the highest wouldn't get as much of a difference in their score. So if you're curious about how it works, please feel free to talk to me. But I liked the recorrection. I like the overall scores based on the recorrection. So I'll be posting the solution guide for you guys to look over in a little bit. On that front though, so once you look at the review guide, please make sure that everything makes sense. So what I mean by that is there should be a score on each problem, and I want those to make sure they're reflected. Make sure that the number at the bottom of the page of each page has been correctly transferred, is first off correct, and then it's been correctly transferred to the front page. As long as all that lines up, we're cool. And then if you think that I graded anything unfairly, or if you think that like you should have received more points, please let me know. The worst thing I can say is no. But I won't say no without any explanation. I'll give you an explanation as to why I'm saying no. So that is what I wanted to say about that. Any questions? We go on to a completely randomly, this is the kitchen sink as we're talking about. As a little kind of brief from little, maybe just a fun little no, not that one. I want this one. If I gave you, and so you don't need to write this down, this is just for a little like pop vocal quiz. Angle A is equal to 37 degrees, lowercase b is equal to 6, and A is equal to 5. Would you use law of sines or law of cosines? Law of sines, because you know everything about one letter. If I knew angle A is equal to 16 degrees, angle B is equal to 45 degrees, and C is equal to 10, what would you use? It's law of sines. It's law of sines. This is that tricksy case, right? That's that little tricksy problem where the fact is we do know everything about C, we just haven't mentioned it. We know everything about C, we just haven't mentioned it, because by this information, we know that angle C is equal to 180 minus 16 minus 45.
But would it also be possible for a lot of content to just, like, I know it's going to be a lot long, but it's still possible to solve it, right?
Sadly, no.
No?
Because law of sines, you need there's none of the equations for law of cosines have two angles involved. There's two side lengths and an angle involved to find another side length.
Usually, if we use the law of cosines, like for example, if side B and angle D aren't given, it's only one.
Say it again.
It's like we use the law of sines if side B and angle B are given.
Yes, that's correct. If you know everything about one of the letters, both the angle and the side, use law of sines. And I was encountering something that I had never really encountered before, which is why law of cosines. You cannot switch to law of sines, actually. Most of the time, it will work out. Most of the time it will work out. but there are a few cases, random cases, where it will try to give you an extra triangle that doesn't exist because of the limitations of cosine inverse and sine inverse. There are a few situations. It's very rare, very seldom that it happens. But on occasion, if you start law of cosines problem, you switch to law of sines, it won't give you a valid triangle. It won't work. And it has to do with the inverse sine versus the inverse cosine. So if you start a law of cosines problem, keep doing law of cosines. Just to be safe. I will make sure on the exam that my example doesn't do that, but on your Alex, there might be a couple occasions where that has happened. Yes.
I think I ran into one of those with Alex. Are you saying it's because it might give you two solutions, like an SSA case?
Yes, like a side angle case. Yeah, it basically it throws things off quite a lot.
I was gonna ask you about that today, how if you start with cosines, if you're doing like side,
Mhm.
and you solve the first one, and then you switch to it. What I found is there were a couple cases where it did give you, there were two different options,
Yes.
but couldn't you just, in one of the cases, I was able to, if the second option didn't work.
Yes.
But
And
the first one did, but I had to solve them both and then figure out.
exactly right. So what typically happens is because of the domain restrictions of cosine inverse and sine inverse, and then they're not linked. What ends up happening is when you find the other angle, when you find your first angle, when you're trying to find the other two, it could be that it's the smaller choice, or it could be the one that's in the other quadrant. And there's like, at least to my knowledge, there's no way to know which one's correct.
The only way that I was thinking is the ratio of the information that you knew, because you knew all the sides,
Mhm.
is you knew the ratio looked wrong compared to the other ones.
True. Yeah. That would probably be the only like kind of giveaway factor, would be like looking at the angle ratio of those
And
things.
also, after solving that one, can't you just check the actual ratio on all, side angle over side? That ratio on every single solution, and see if they all match, and if they don't, then you know which one.
Yeah, I think that would be the case. It ends up taking a little bit longer, but yeah, that probably would work out. Yes, I haven't really, but that's a good point.
Can you, just start with, sign of, laws and stuff, sign, like, go to cosines?
I believe you can on that front. I think you can go from law of sines to law of cosines, but
Because it worked for me on the others, I was wondering.
because it did work.
Yeah, it did work, I'm asking if it would work in any situation.
So going from like starting with law of cosines problem, it doesn't happen very often. It's few and far between, but every once in a while it does throw things off. So, okay. Any other questions before we get started? Yes, Eli.
So you're just saying that we can't use like low cosine, low sine?
Yeah, don't go from law of cosine to law of
It's on
sine.
the paper, thanks.
Yeah, on the paper exam. I'm gonna try and make sure that it's not like that situation doesn't happen, just because I don't want to run into that situation. But it's best practice to do that. Okay. So we get to a very, 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 very useful concept. If you plan on taking Calc 3, you will use polar coordinates quite a bit. If you take Calc 2, you will probably see a little bit of it, like at the very, very end of the section. And then if you go beyond that, you'll start to see the utility of polar coordinates. So, important thing to understand, this is the same thing. When it comes to talking about like what a coordinate system is, it's a way to describe where a point is. And so what I can think of is in our rectangular coordinate system, imagine Vegas is very, very grid-like. It's perfect for this analogy. If I want to get to my friend who lives across town, I might have to go up 5 miles to Charleston or whatever, and then turn left 6 miles and find him. So like imagine that means I was right here, here's my friend, and I go up several blocks and then I go over several blocks, and that's how I find him. Or vice versa, or I could have gone the other way. I could have turned right and this one, but based on traffic, it might have been better to go up first. So that is one way to describe it. But if you're able to walk through walls, or if you're able to drive through walls like the people in the Matrix Revolutions, right? That it's a no, not Revolutions. Reloaded, second one, the worst one. That one was bad. But they had those cool guys that were like able to go through things. They're invisible, right? And so if you were able to do that, what you could do instead of being right here, you could say, well, my friend is about a 30-degree angle up here. And so all I need to do is just find him by going straight across this line. So at the end of the day, a rectangular coordinate system and a polar coordinate system, there are two ways to describe the exact same point, just in different operations. So with a rectangular grid, we have a horizontal distance from the origin and then a vertical distance from the origin, and that's how we find our points. Whereas with with a polar coordinate system, excuse me, I need to move stuff all around. With a polar coordinate system, we describe him as a point with a distance from the origin as a radius, essentially, and then an angle theta from the positive axis, which we call the polar axis, which we just, by convention, we started at the origin and we moved to the right. In an alternate reality, we maybe are looking at this thing, and maybe we made it go to the left. But as it stands, we like to do it the way it looks here. I think it's it. I want to make sure I didn't want to write any extra notes here. So a polar graphing grid, it looks different, but it's the exact same thing. You can map them onto each other. So, which means that there is a one-to-one correspondence between these two things. There's a way to describe things rectangularly, and there's a way to describe things polarly, and they can give you the exact same point. So the origin is always the origin, because like that's what when we created a coordinate system, whatever it may be, we have to have like a point of reference. So instead of being an x comma y, it's an r comma theta. And that might seem like a very, very random and useless thing. However, because of the properties, where did my pen go? Where did it go? Did it fall? Go. There it is. Thank you. I don't know who I said thank you to, but I said thank you. Okay. So they're just two different ways to identify the same points in different ways. And they're very, very closely connected. And the point being is that there are certain things in mathematics that are impossible or near impossible to do in a rectangular coordinate system, but they become very, very quick and easy in a polar coordinate system. So just to give you, I mean, this is going to look like gibberish a little bit, but in Calc 2, you might be tasked with finding the area, the volume under the curve e to the negative x squared minus y squared dx dy. And as it currently stands, this is basically a very, very challenging problem to do. I did it one time, and it took me a full page to do it. And actually my TA, when they graded it, said, "Did you even try converting to polar?" Because he was pissed off at how long it took. And like I was correct, but it took way too long. Whereas if you can convert to polar, this becomes the double integral of e to the negative r squared r dr d theta. And I know this once again, this looks like gibberish, but this e to the negative r squared r dr d theta is so much faster to calculate. It is so much faster to calculate. And you'll see that once you get to 283. It's going to look like nothing right now, but it's a very, very useful thing. It's to describe things polarly. Additionally, there are curves that exist in the plane that are not possible to really graph without writing a nuance of awful stuff in rectangular coordinates. But as soon as you switch to polar, it becomes very fast. So that's kind of the brief rundown. It is an important system. It will come up time and time again. You start off in Math 283 talking about polar coordinates and polar, shifting to polar, and then you'll start talking about spherical coordinates and so on and so forth. They're very useful things. So how do we plot points in this system? So if r is positive, you just move out towards the angle that you've created. And theta, like the good news is the angle is exactly the way we've described it so far. If the angle is positive, we're going to rotate counterclockwise because that's what we've always done. If theta is negative, we're going to rotate clockwise because that's how we draw negative angles. And so the question is, what happens if R is negative? So when you're trying to convert from rectangular to coordinate, your R value will almost always be positive. But it is possible for R to be negative. And all that means is instead of going out a positive direction from the angle, you're going to go in the backwards direction. So I've got an example right here. So with a positive R and a positive theta, you just start with your polar axis, which is the right half of your x-axis. Find your theta, and then go out a distance of R to plot that point. If your theta is negative, then you're going to go regular clockwise, or just clockwise to that point, and then go a distance of R out to plot it. So for example, if I want to plot the point R of theta equals 4, 3 pi over 4, go 3 pi over 4, and then go out 1, 2 units, 3 units, 4 units to get to it. Then if I want to plot the point 4, negative 3/4, I go negative 3/4, and then go 1, 2, 3, 4 to plot that point. So with rectangular coordinates, it was a lot easier to choose. You could start with X or Y to find the point, right? With polar, it's usually best to start with the angle first. So why isn't it theta, R? I don't know. I think it was just a convention. And so here's a situation of a negative R, theta. So you go out your theta. This is your angle line. And instead of going out a distance of R in the forward direction, you're going to go in the backwards direction. And so here's a negative theta, negative R. So we go out negative theta. So we go clockwise. And then we extend this line backwards and go a distance of R out this way. That would be negative R. So for example, if I've got the point negative 4, 3/4, I find the angle line for 3/4, which is right there. And then I extend the line and I go backwards 4. So 1, 2, 3, 4, and that's where that point is. And then if I've got a -1 and a negative, so negative 3 pi over 4 will be right here. And then I extend the dashed line further and I just go backwards 4. 1, 2, 3, 4, and plot that point. So that's how we plot in rectangular coordinates. Is start with the theta, then use the R. If R is positive, go forward. If R is negative, go in the backwards direction along that same line. Any questions on that? Let's get to plotting them. Let's get to practicing. So 4 and then 5 pi over 6. That's positive R and a positive theta. So we'll find out where 5 pi over 6 is. That's going to be in the second quadrant. So we'll go all the way over to 5 pi over 6 and draw our radial line, our angle line. And then we want to go out 4 units. So 1, 2, 3, 4. So right there. 1, 2, 3, 4. Yep. Right there. That is the point 4, 5 pi over 6. This next one is negative 5, 5 pi over 3. So R is negative. So we're going to go the opposite direction of the angle. Go opposite direction of the angle.
First one, is this 4?
Say what?
Is this 4? Should be like the third line.
So there's 1, 2, 3, 4. It's hard to see probably from over there. I'm going to zoom in actually. So there's a small inner circle, 1, 2, 3, 4. That's where it is. Next one, 5 pi over 3. That's in the fourth quadrant because that's 1 less than 6 pi over 3, which is 2 pi. So we'll do that right to there. That's 5 pi over 3. And so what we'll do is we'll go backwards to find it. Go back 5. 1, 2, 3, 4, 5 to right there. And that is negative 5, 5 pi over 3. for TA actually said that at one point when I was working at OSU as a TA, and one of my colleagues said, "Oh, you can't have a negative R." I was like, "Ooh, gotta change that. We gotta make sure we talk about that during the next TA meeting." By the way, there is such a thing as a negative R. It seems kind of counterintuitive because whenever we think of R, we think of radii, and radii are intrinsically positive. But my statement has always been, if we're thinking about something that's physical in nature, something that's truly a physical property, then yes, we can't have negative values. But this is a mathematical object in its creation, and mathematical objects can be positive or negative. Jake, and then Brian.
Seems like you don't have a convention on which, if you use the dotted line to go backwards, or in the examples, you were using the dotted line to show. Does it matter?
It doesn't matter, no. Like you can even use a straight line to figure it out, the whole thing. Yeah. It does I like to find the angle first and then do the dash. I change my mind every once in a while.
Okay.
And then Brian.
That was kind of the same question.
Okay.
So if the dotted line was solid.
Mhm.
That's fine.
That's fine too.
As long as, but what if you see where the bottom half of it, what if that was just gone?
If that was gone, that'd be fine too.
As long as you say it,
Yes,
because otherwise it'll look great.
exactly right. So the thing is, and the line, honestly, it really even shouldn't be there. At the end of the day, once you get really good at this, you don't need to do that. You just plot them, just like we did with rectangular coordinates, right? I don't do when I need to plot the point 3, 4, I don't go over 3 and then go up 4 and plot this point. I don't draw the lines. I just know where to plot it, right? In a similar fashion, once you get comfortable enough, you could actually do this without plotting those lines and stuff. It never hurts to draw them as you're starting out and on an exam, because if there is a problem like this, then you can get the full credit by it. Like you can get partial credit, but at the end of the day, if you don't draw it and you plot the right point, you'll get full credit. -3 comma pi over 2. So once again, the R is -3. R is negative. So go backwards. So pi over 2. That's just going to be up to here. It's not going to let me do a nice line. There we go. Cool. And then we're going to go backwards 3. Right there. Actually, that's what I'm going to do. I'm just going to make the dotted line to go. I just keep changing my mind. I just keep having fun. So that was the original angle line, but it's a negative R value. So we're going to go backwards 1, 2, 3, and plot that point right there. That is -3 comma pi over 2. The next 3, I'd like you guys to plot. I will slowly fill in details. So I'd like you to try and do it yourself. And if you feel comfortable like imagining where the line will be and counting it, that's fine too. This is really for our note-taking purposes to look at it and how it's coming to be. So because it's a pi over 6. Yes, yes. Okay. I have them up here. Still work, are we still working on them? Are some people still working on them? Are we ready to go over them? I'll let people work a little bit longer. I'm going to put them, all 3 of them up here, even though it's hard to see. I'm going to pass back the last a couple exams. People came in. Who won? Who won? 12. Max. Max here. Neil. Alex here. 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 Brian. Here. John Loza. Good. Oh, Pedro, you're here. You get it. Didn't you? Okay, so to go over them real quick. The first one, it has a negative theta. So that is the problem with having these lines being measured from 0 to 2 pi, is that it's kind of can throw us off a little bit. But negative 3 pi over 4. So we got to go 1 pi over 4, 2 pi's over 4, which is negative pi over 2, and then an additional pi over 4 to give me that negative 3 pi over 4. And the radius is positive, so we're just going to go 2 tick marks up and plot that point. Next one, negative 6 coming negative 5 pi over 6. So it's both a negative r and a negative theta. So we've got to go 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5 theta over 6s to get to the negative 5 pi over 6. And then we're going to extend the line backwards because it's a negative r out to 6. So 1, 2, 3, 4, 5, 6. And last but not least was this one, which was the tricky one. Your theta value is larger than 2 pi. 2 pi in terms of thirds is 6 pi over 3. So this is 5/3 larger than that. So it requires 1 rotation and then an additional 5 pi over 3. So 5 pi over 3 is your coterminal angle. So 1 rotation in green, then an additional 5 pi over 3 rotations to get here. R value is positive 7. So we just go straight through the line to get to that point at 11 pi over 3, 7. Any questions on that? So, given the fact that we can have coterminal angles, that would mean that we can have a point represented in infinitely many ways, because you can just keep adding an additional 2 pi, but you can also subtract pi's and make your r values negative. So for example, I could do 5 comma 3 pi over 2 to get that first example here. I go 3 pi over 2, and then I go down 5 to get that point. But I could also go negative pi over 2 and get the same point. But I could also make my r value positive and go to pi over 2 and then go back 5 and get the same point. That's 3 of them, but there are infinitely many, because any of those ones now I could just add 2 pi or subtract 2 pi and get more and more of the same points. So there are 2 ways that I was just suggesting. You could either leave r alone, keep the r value the same, and then just keep adding 2 pi's. So for example, if I got the 5 pi comma 3, 5 comma 3 pi over 2, I could subtract 2 pi, which is the same thing as subtracting, by the way, just so we're constantly reminded, that's 4 pi over 2. And that's why I get negative pi over 2, and that, behold, is another point. But I could also add 2 pi, as I did here. And once again, that's 4 pi over 2. So adding that will give me 7 pi over 2, and I get another point. You just keep doing that over and over and over again. Exactly right. Or you can make r opposite side, which make it go backwards. And so in order to counterbalance that, we can add or subtract pi. If we want to change, like if we want to use a negative r, we just need to make sure that we add or subtract pi because it's on the same radial line. Like every single time, this is a distance of pi. All right, angle change of pi. So we can make the r value negative and subtract pi to bring us up to here. And so negative 5 comma pi over 2 is the same point. There are multiple ways to do this. And so that's kind of one of the fun things, is that there's always a way to write it. The difference between the rectangular coordinate system, though, we can only write the coordinate, that coordinate point in one way. But here, because we're dealing with angles, we can do it in a lot of different ways. And this allows us to graph things, by the way, because this thing kind of like rotates around 360 over and over and over again. This allows us to graph some really, really cool things. There's a thing called a rose curve, which is not really very feasible to draw in, let me get a nice, do I have an extra coordinate? I'll just erase this one for a second that we drew on already. There's a thing called a rose curve. And what that looks like is like this. It looks really, really fun. I didn't draw it perfectly, but it's a very, very fun one. You can even do like that's a 3-petaled rose curve. You can get a 4-petaled rose curve that looks like this. Very, very terrible. I've never been able to draw them properly. It's always been my kryptonite. I think they go like that. Yeah, like no. No. That's right. Okay, it's like that. It's not perfect. It doesn't matter. There are things that you can draw that are very, very cool that can only be drawn with polar coordinates. So find 2 additional polar representations of each of the following Portland quarks. Write each one in the simplest form with an angle between negative pi over 2 and pi over 2. So for here, just because it's going to be useful for reference, negative pi over negative 2 pi to 2 pi would be equal to negative 10 pi over 5 to 10 pi over 5. So this first one, I'm going to try and do it just by changing the angle. Add, subtract pi. Sorry, 2 pi. And for this one, I'm going to do opposite r and add slash subtract pi. So the reason why I say add and subtract is if we're given a specific stipulation, like in this problem, we can't add 2 pi. You can only subtract 2 pi. Because as soon as we here, we can't add 2 pi because that will take us out of it, of bracket negative 2 pi to 2 pi. Since our value is already positive, if I add 2 pi to it, I'm always going to get a number that's larger than 2 pi, right? I've got pi over 3, 4 pi over 5. If I add 2 pi to that, it's now going to be 14 pi over 5, which is outside of the range. So we're just going to subtract 2 pi. So 5 comma 4 pi over 5 minus 2 pi, which is 10 pi over 5. And that'll be comma 5 comma negative 6 pi over 5. And that's an equivalent point. And its value, like negative 6 pi, that is greater than negative 10 pi over 5, which is negative 2 pi, so we're good. So the other one, and this one, because adding pi or subtracting pi to 4 pi over 5 will not put us outside of 2 pi or outside of negative 2 pi, right? Because we're only adding 1 pi. If as soon as we added 2 pi, that was the problem. If we were to subtract 2 pi, it worked out. But anyways, so this one will make it a negative 5 now. And we'll take that 4 pi over 5, and we could add pi to give us negative 5 comma 9 pi over 5, which is in, or you could do negative 5, 4 pi over 5 minus pi, and get negative 5 comma negative pi over 5. Yep. Either one would be fine. Yes, Brian. Excellent question. So one way to do, like, there are 2 different ways you can do it. One of them just involves finding coterminal angles. Adding 2 pi's will always find a new angle with the same exact location, like same exact angle line, and you can use that. That is one way to do it. But since r can become positive or negative, the other way to do it is to make it the opposite sign. And so it's not shown here, but this line, if you were to extend it over here, it's always a pi away from it. Is it showing up now? No, it didn't show up very well. That. You could either subtract pi minus pi. So 3 pi over 2 minus pi, that gives me pi over 2. Or I could add an additional pi. Let's use green. No, let's use orange. Or I could add pi to give me 5 pi over 2, and then just make my r negative, and it would push it, it would shift it down where it needs to be. Does that make sense? Yes, great question. So, yes.
On the upper right, is that 9 pi over 5?
That is an alien. That is a 9. Very, very bad 9.
Yeah, when we change the radius from positive to negative.
That's correct.
Or negative.
Because that way we're going on the same line, the diameter line that we're going through. All right, I'll do another one, and then we will. Oh, could have made this worse. I could have made this more fun. By instead of like writing it as negative 3 comma negative 6. So negative 6 is a radian measurement. And how would we find that? That'd be fun. But we'll get to that. So this one, negative 3 comma 10 pi over 7. So here, negative 2 pi to 2 pi will equal negative 14 pi over 7 to 14 pi over 7. Sorry, I know that's hard to write. Maybe write it on the side with the very little space that's allowed. But just as a reminder, so I can't add 2 pi to this one. Because as soon as I do that, I will get outside of the 2 pi range. I'll be adding 14 pi over 7, and that'll get to me to 24 pi over 7. So it won't work. So I have to subtract 2 pi. So this would become -3 and then 10 pi over 7 minus 2 pi, which will give me -3 comma, that's 14 pi over 7. So -4 pi over -4 pi over 7. And then if we make it the opposite r, if we added pi, would we be still in the area? In the interval? No, because if we added pi, that'd be adding 7 pi over 7, and that would put me at 17 pi, which isn't in the interval. So, so we'll do +3 now, and then it'll be 10 pi over 7 minus pi, which will give me 3 comma 3 pi over 7. So once again, I can't add pi in this case because that would put me outside of the interval that's desired.
Change the 3 to a positive.
Because if I'm going to be adding or subtracting pi, that's going to put me onto the opposite side of that diameter line. And that's so in order to get me back to where I need to be, I have to change the sign of the r value. So opposite sign. So since it was started off as a -3, flipping it would make it a +3. Right, I'd like you guys to do the next two. Find a good choice, and I will slowly fill in the details. The answers up here if you'd like to check your work. I'm gonna go over in just a moment. So, any questions before I get started with the explanation? So, we want to, oh, Marcus, yes.
The bottom, it's not two solutions, just because.
Just because. Yeah, you only have to find one. I was just saying either one would work. Yes. So and I'll talk about that once we get to that one. So I'm always writing what negative 2 pi to 2 pi is in terms of my denominator, just because it will make it easier to know whether or not I get outside of the range or not by adding or subtracting 2 pi. So with that one, it's got a negative 11 pi over 8. So if I were to subtract 2 pi, that wouldn't work because that would get me over at negative 27 pi over 8, which is outside of the range. So I can only add 2 pi in this case. So I add 2 pi, keep the radius the same. I'm just finding a new coterminal angle. Negative 11 pi over 8 plus 2 pi, which is really 16 pi over 8. That gives me 5 pi over 8. Right, yes. Oh, you're just stretching? Okay, Basil, yes.
I noticed that for, once you change the R, like from negative to positive, vice versa.
Yes, for the second option. Just for the second option, because that's the one where I'm trying to change the angle, but making the R negative so that it would flip onto the other side of that angle. So, and the thing is, if I want to find 2 more points, I'm kind of forced. I'm pigeonholed into this property, this situation, because I can't really figure out it. Like not pigeonhole. That's a different mathematical concept. I'm forced to do this method to get another point in the same pi interval or the same theta interval. The bottom one, so negative 2 pi to 2 pi would be negative 18 pi over 9 to 18 pi over 9. So because it's a negative pi over 9, if I subtracted 2 pi, once again, I get outside of my interval because I'm taking a negative number and subtracting 2 pi, that'll make me definitely less than negative 2 pi. So I can only add 2 pi to get me another angle. And that's really 18 pi over 9. So negative pi over 9 plus 18 pi over 9 gives you that 17 pi over 9. And then for the third, for the other option, I would have to change the sign to flip the direction of the R, making it positive 2. And then if I add pi, I will stay in the interval. But if I also subtract pi, in this case, I will work. In the second, in the previous one, with the adding of the pi, I can't subtract pi because then that will make me go outside of negative 16 pi over 2 or 16 pi over 8. Any questions on that? So right now, in my opinion, what the best thing for us to do so I could go further and further in more detail into polar coordinates than I am going into, but I don't want, I want this to be how we work with it right now. 182, you'll start to work with how to convert to polar, and that will be fine. Right.
So could there ever be 2 solutions for first box, or is it always going to be that you add 2 pi or you subtract 2 pi?
In this case, because it's only from negative 2 pi to 2 pi, yes, you can only do one of them.
Okay.
If it was saying from negative 4 pi to 4 pi, then you might be able to do an add, a subtract, or maybe a 2 add. Like you may be able to add 2 pi twice. All right. So we cannot, not only can we just find multiple points, we can be given requirements on R and theta and to work through it. So we need R to be positive. And so that means we have to switch R. Since R is negative, since initial R is negative, we need to flip. Change sign. So we'll add, subtract pi after that as well. Let's talk about that, what I mean after writing it down. Our initial R value is negative, but we want it to be positive. So in order to get to the corresponding point, we will need to make sure we add a pi or a negative pi. It's like add a pi or subtract a pi to get us back to where we want to belong. So if I were to add pi, that would get me outside of the interval. Because it's 7 pi over 4, which is 1 pi less than 2 pi. 1 pi over 4 less than 2 pi. So I'm going to subtract. So we got positive 6 comma 7 pi over 4 minus pi, which gives me 6 comma 3 pi over 4. Because we don't want to exceed 8 pi over 4 and we don't want to go negative. Any questions? Oh, Alex, yes.
I'm not certain if this is gonna be a format on a test or a quiz, but is that notation help you technically get partial credit?
Yeah.
Because I just tried to solve it in my head and I realized that was a problem if I did make a mistake that you would want to see that.
Yes, but I mean, it's like as you get better and better at this, you don't necessarily need to write down this work. This is mainly the I mean, I've said this over and over again in this class, but and I'm sorry it sounds like a broken record, but like when I write notes, this is for us to look back on so we know what we did. So like when you're like, because if we just wrote the answer, right? If we just did this, if we got rid of this portion and maybe even this portion, you're like, how did I find it? Like you'd be looking back over your notes and you might be like, you might remember by looking at the other stuff, but at the same time, like it might be like, what was going on? This one. So we're given 7 comma 5 pi over 6, an equivalent polar coordinate where r is greater than 0 and theta is between negative 2 pi and 0. So for this one, my r value needs to stay the same. My r value needs to stay the same, which means I have to add / subtract 2 pi to get coterminal angle. I'm saying it in general terms because like it could be that you need to add 2 pi. It could mean that you need to subtract 2 pi. So we don't know yet, but we know that since we keep our r the same, the only way to get an equivalent point would just to be to add 2 pi to find a coterminal angle and get back to where we started. That's what we'll do. In this case, adding 2 pi would not work out because that would put me beyond 0. That would just put me further. So I'm going to have to subtract 2 pi. So we've got 7 comma 5 pi over 6, and we're going to subtract 2 pi, which you can always write this if you'd like. This is negative 12 pi over 6. This becomes 7 comma negative 7 pi over 6. The last one.
Other way with the second part.
For the second one?
Yeah.
For the one we just did? We can do like the negative r.
Yeah.
Well, unfortunately, no, we cannot. Because we're requiring that r needs to be positive. So if we made r negative, now this would be negative and it wouldn't be the format we wanted in. See, like this feels like a really like I dislike these problems. I think it's a good problem, the fact of trying to make sure we're thinking critically about how to manipulate the stuff right and do the way we want it to be. But it does seem a little bit tedious at some points, right? It seems like a teacher saying, you gotta rationalize your denominator. You gotta do that thing. Or You gotta simplify your fraction. You really want me to simplify 1,265 over 459? Is there anything there? Do I really want me to do that? Because I don't want to. Okay. I'd like you guys to do the last problem. It's tricky, by the way. It's tricky. Okay, that one's tricky. You're still working on it, continue to do so. It's but I want to talk through this one because this one was tricky. So we need to change the R value to negative because it's we've already got a positive R, but we want a negative R. And so if we change it to a negative R, the only way to get an equivalent point would be to add or subtract pi. Because now if we were to add a 2 pi, then we would just get to the same angle, but we'd be on the opposite side because we'd be moving backwards. So we just add or subtract a pi. Now, if we were to subtract a pi, we get further and further away from 0 to 2 pi, so I'm going to have to add a pi. And when I do that, I get -1 comma -4 pi over 3. But that's not in the interval, the desired interval. So we need to do something else. Now, I don't want to change my R value because if I do that, then my R value will be positive. So I have to find another equivalent point. And this time I'll use the coterminalness because I'm going to keep my R value negative. So the only way to find another point would be to add or subtract 2 pi. We're not going to subtract because that would get me further away from the interval, the desired interval. So I'll add 2 pi. And so when I do that, I get -1 comma 2 pi over 3. That's that tricky case. Feels like a two-parter. Brian. That's fine too. As long as it gets you the right point, I'm pleased. As long as it's being done mathematically validly, yeah, that's fine. Good point. Yeah, you could add 3 pi, which is 9 pi over 3. And that's really the equivalent of adding a 2 pi and then an additional pi. So you have to change the R value. Yes, absolutely.
So then if you ever have this case where you have to change from positive to negative.
Or negative to positive, yes.
On the R value, you can, like, let's say if we just added 2 pi, that would have gotten us to the range. Is that, or it will never be added?
If you're changing the R value, it should probably start off by like adding or subtracting the pi.
But like, could it ever be add 2 pi?
And change the R value?
Yeah.
No, because then what that will do is it's a great question. So let me grab one of these points just for a quick second. So let's just say here's my R theta, right? Right here. If I add 2 pi, right, that's that. If I add 2 pi to it, it would go all the way around and then to there, right? But if I make it so this would be R comma theta plus 2 pi. But if I make it negative, or let's use blue, let's zoom in a lot. If I make it negative, now instead of being here, it's over here. So it will, like, if you add 2 pi, you're always going to find a point that's directly opposite of it on the diagonal, on the diameter line. Is that okay? So adding a 2 pi will make sure, like, it'll give you the same angle, but now if you make your r negative, now it gets pushed backwards or forwards, depending on the situation. If it was down here, it get pushed forwards.
So then when you cut that pi, it takes it to where?
Yes, if you add an additional pi, it will work out. Is that what was I misunderstanding your question?
Where I was just seeing why the 2 pi doesn't work.
Yes. So if you do that, then you just all you need to do is just add an additional pi and it'll get you where you need to go. So yes. Okay. And then now we get to talk about the fun thing. Is I told you at the very beginning that these things are the same way of talking about these things. We're talking about the same thing. We're talking, if we talk about it rectangularly or polar coordinately, they're the exact same thing, just two different ways to say it. Tomato, tomato, essentially. And so the reason why we introduce it now is because of the fact that we can draw triangles to find these things. That's how we found distance back in the day, is like when we were learning about the distance formula, it was all about drawing triangles, but we can also do that here. And so if you want to find the XY coordinate, you can think of it as a triangle here, where this is the hypotenuse, and then you have the unknown side lengths, but that's your X and your Y values. But you can use trigonometry to find them, right? So if this is Y, this is your Y value, or no, let's use red. This is your Y value, and this is your X value, because you can impose a coordinate grid on it too. That's why I've drawn the XY grid right there, in addition to the polar grid. And so, cosine of theta is equal to X over R, and sine of theta is equal to Y over R. So that means that Y is equal to that, and X is equal to R cosine theta. So that is the conversion ratio, is that if you want to convert from polar to rectangular, you take your R and your cosine theta to get your X, and you take R and sine theta to get your Y value. So this is a nice little nifty chart to represent it. So we're going to convert to polar, and then plot the point in rectangular coordinates. So R is -3, and theta is equal to pi over 3. And just as a small little note, what quadrant are we in? Pi over 3, pi over 3 would be in quadrant 1. But it's -3, so it gets shifted to, so we're in quadrant 3. Point is in quadrant 3. So we want to make sure that if we get something wonky happening, if we make an error in our calculations, or maybe we forget to change our calculator from radians to degrees, and you start getting a point that's in quadrant 1 or quadrant 4 or quadrant 2, that would be a good indication that you made an error. So X will equal R cosine theta. So that will equal -3 cosine of pi over 3, which if you plug that into your calculator, you should get -3/2. And then Y will equal R sine theta. So that'll be -3 sine of pi over 3, which will be -3 square root 3 over 2. And that is a point in quadrant 3. It has a negative X value and negative Y value. That's why in the beginning of the semester, right, we had those questions on the exam, like on the homework that was like, what quadrant will a point be in if X is negative and Y is negative? Good thing to check. Since we got it in quadrant 3 again, we know we're correct. So the point is -3/2 comma -3 square root 3 over 2. Any questions on that? I'd like you to do the next two problems. The good news about converting from polar to rectangular is that there's no needing to worry. Like, it's mainly the quadrant 3 thing is just checking our work. And it's always a good idea to rewrite the equation, like the formula each time. It's just a free way to memorize it. It's free memorization. Right. All right. Let's see you again. All right, I've got the answers up here if you'd like to check your work. I made a small, like if you're following along, just make sure you didn't, like, I made a small boo-boo. I said the cosine of theta, cosine of negative pi over 4 was negative square root 2 of 2 at first. A little mishap. But just a straight plug and chug. And the reason why this is very, very nice is that there's only one way to represent a point in rectangular coordinates. There's only one way to represent it, and so it always works out this way. And that's nice. Are there any questions on these ones? Going backward. Oh, yes, Marcus.
My calculator, it just didn't put it exact like yours. I'm wondering if there's a method for me to find the exact value of it.
You have to use cosine square root and then multiply that by whatever. Like, for example, if it's like,
Oh, yours, you're using that calculator. So that one, ask me for a calculator on the exam. The TI, that one is fine enough for most situations. It really is. It gets it gets the job done. But the Casio is just like, or the TI 30XIIS, or 31 or whatever it is, the next up model is. This is 30. Oh, that's the 30XIS. Then it's the TI 30XS. Okay, that one's just a better one. It's just. So just ask me. I'll have two calculators on me. So just, and then I'll bring a sword in case anybody else grabs one, so you guys can duke it out. Put it right in the middle. Do a little Joker situation. Okay. So how do we go about finding a point if we're going backwards? So that means we're given given x comma y, want r comma theta. So in essence, the reason why it's going to be that x squared plus y squared is equal to r squared and tangent of theta is equal to x over y, I'd like to show it. We have this point. Let's call it x comma y. And what we can do is we want to find r, right? And we want to find theta. Well, to find theta, we can think of it like a triangle. Tangent of theta equals x, y over x. But to find out what r is, we can't use a triangle because there's too many unknowns. You could relate it and stuff, and you probably would find out something, but you can think of it like a point on a circle. A unit circle, or not a unit circle, but a circle centered at the origin. So then this means that x squared plus y squared is equal to r squared. So the problem, the reason why we're not using theta to find out what r is that there's too many variables involved. I suppose you could go through and say sine of theta is equal to y over r. So you could solve it in a very, very strange roundabout way, but the best way is to use the r value there using the unit circle approach. So you'll notice that I have points in quadrant 1 and 4 versus points in quadrant 2 and 3. Because you're going to be using inverse tangent to find theta, and inverse tangent only produces angles between negative pi over 2 and pi over 2, we have to be a little bit careful. Because if our thing was in quadrant 3 or quadrant 4, then our angle wouldn't work out. It would be trying to give us a point in the first or the fourth quadrant. So if you're in the first and the fourth quadrant, it's no problem. If you're in the second or third, you can do it in a myriad of ways, just like we did with these other ones. You can find it in a lot of different ways. So you can either keep r positive and then subtract or add 180 degrees or 2 pi to move the angle into the opposite direction, or you could keep the theta the same and then just make the r the negative version of it, because that would just push you into the correct quadrant. It would push you in the opposite direction. So those are the two ways you can do it. So for example, consider the point -9 comma +1. So we can find r. It's going to be the square root of 9 squared plus 1 squared. That's the square root of 82, which is roughly 9.06. And then if you do the theta, which would be find the theta, tangent inverse of y over x, so 1 over -9, that gives you -6.34. But the point -9,1 is in the second quadrant. So we could just add 180 to get me over to where I need to go. So, I mean, we can even draw that just a smidgen if you'd like. Just a little baby graph. Draw that just a smidgen. That doesn't make any sense. That's not a real statement. So I don't know what I'm saying. That's true most days. So that's negative 6.34 degrees. And we want to go over to here where the point 9, 1 actually is. So we'll add pi. We'll add 180 degrees. Or we can just leave the theta alone, keep it at negative 6 pi over 3, and then just go backwards. Is that okay? Any questions on that? So you need to check what your quadrant is. And so the reason, once again, the reason why this one's not as nice is because we're trying to go from a coordinate system where there is only one option to write a point into a place where there are a myriad of ways to do it. That's the reason, plus the fact that tangent only produces angles between negative pi over 2 and pi over 2. And this time we usually like to write them in degrees because they're usually very rarely ever nice angles. Okay. Looking at the time, we don't have enough time to finish these ones, but we will pick up next time with these ones and then go into vectors, the other part of the random side notes. Okay, guys. If you didn't get your exam, did anybody not get their exam? So once again, please look over it, make sure that everything's adding up correctly. And if anything isn't, let me know and I can fix that immediately. Otherwise, feel free to talk to me about whether or not you think something was graded unfairly, and I'm happy to go over it with you and maybe give you back points. You never know. If you have any questions, feel free to email me. Otherwise, I'll see you guys on Wednesday.